This is the video lecture over section 2.7, where we'll be looking at the measures of the spread of data. Where the previous lecture was about measures of center, averages, section 2.7 is going to deal with a different way to describe sets of data by quantifying how spread out or close together their values are. Let's begin by looking at an example where the measures of center don't do a very good job of distinguishing between two sets, but you can tell that they're different in some way. Here I have exam scores listed for two students, Dante and Randall. You can see Dante scored a 75 on exam 1, a 78 on exam 2, and a 72 on exam 3. Dante's scores are very consistent and close together. Randall, on the other hand, is much more spread out and varied. Randall scored a 98 on exam 1, a 52 on exam 2, and a 75 on exam 3. You can tell these data sets are different, but if we were to look at them from the perspective of measures of center, you wouldn't see any difference. For example, if I find the mean for Dante, adding those three scores together and dividing by 3, I get a mean of 75. I encourage you to check that either by working the mean by hand or by using your calculator. If you find the median, ordering these from smallest to largest and then find the number in the center, that's also 75. Let's do the same for Randall. If you were to find the mean for Randall, add those three scores together and divide by 3, you get a mean of 75. Exact same mean as Dante. And if you were to order Randall's scores from smallest to largest and find the median of his scores, you get a median of 75. The mean and median are the same for both of these students. So from the perspective of measures of center, you can't tell a difference in these two sets. They have the same mean, they have the same median. Neither has a mode because there's no repetition. From the perspective of the measures of center, you would think that these two sets were identical. But you can tell they're not. Dante's scores are much more consistent and close together. Randall's scores are much more varied and spread out. We can use another kind of measure to describe this difference, and those are what we call measures of variation. A measure of variation is a summarization of data designed to measure the spread of the data set. We use a measure of variation to quantify how spread out or close together the values are. Relatively speaking, a small measure of variation means that the data set is compact, close together, and a large measure of variation indicates that the data is widely dispersed, spread out. So when you calculate a measure of variation for a set that has its values close together, you'll get something relatively small. And when you have a data set that's really spread out, the measures of variation will be pretty large. In this section, we're going to look at two measures of variation. The first of those is a simple one. It's called the range. The range of a collection of data is the difference between the maximum value and the minimum value. So you identify the very biggest value in the set, you identify the very smallest value in the set, and then you literally subtract them and find their difference. We oftentimes use this word range to mean like an interval of values, like the data ranged from this number to that number. That's not how we're using it here. The range is the actual difference. You literally subtract and get a single number, and that single number is your range. Let's go back to the test scores for Dante and Randall and not look at them from the perspective of measures of center, but rather look at this range, a measure of variation. If we find the range for Dante, we identify his largest exam score, which was 78, his smallest exam score, which is 72, and we literally subtract them. The range for Dante's exam scores is 6. So on its own, that tells us that the difference between his largest exam score and smallest exam score is 6 points. But we can also use that to make comparisons between two sets of data. Let's do the same thing for Randall. Randall's largest exam score was 98, and his smallest exam score was 52. To find the range, we actually subtract those, and we get a value of 46. You can see that Randall's range is much larger than Dante's range, indicating that Randall's data is more spread out. On its own, Randall's range tells us that the spread in his test scores is 46 points between the max and the min. But making a comparison, we can just see that Randall's test scores are more spread out than Dante's test scores because Randall has a relatively large measure of variation where Dante has a relatively small measure of variation. So where we couldn't tell the difference in these two sets using measures of center, we can tell the difference using measures of variation. Now this seems like a pretty straightforward and simple way to do things. Why would we complicate it with a nerdier measure? Why would we take this any further? Well, the range is easily swayed by outliers. You could have an example where there's an outlier and it makes the data seem like it's much more spread out than it is on the average. For example, imagine a student who has 5 test scores and 4 of them are in the 90s and then a 5th score was in the low teens because the student just had a bad day. Most of those exam scores are clumped together in the 90s, and then you've got this 5th test score that's significantly smaller than the rest of the data. If you were to just use the range to describe the dispersion of the data, you'd get the wrong impression because most of the data is clumped together. So we have other measures of variation that don't just use the most extreme values but kind of measure from the center. And the one that we're going to talk about is called the standard deviation. In my definition here, you'll notice that I specify that it's a sample standard deviation, but this definition would apply to both a sample and a population. The sample standard deviation is a measure of variation which represents an average distance from a value of the variable to the mean. Rather than measuring from the edges, we're going to find an average distance to the mean, which should be somewhere in the middle. We discussed that sometimes it's not really in the middle. But we choose the mean over the median because of its arithmetic property. Quick bit of notation here. When you're working with sample data and you find a standard deviation, we denote the standard deviation by s, lowercase s. When we're working with population data, we'll use a Greek symbol like we did for means. And I should point out that when you're working with population data, the formula is actually a little bit different. I'll get to that in a moment. First, let's look at the formula for the standard deviation of a sample. And when you see it, it's going to look intimidating. The formula for the sample standard deviation says, find the sample standard deviation by first calculating the deviations from the mean, that is, take each value of the variable and subtract the mean. Then square all of those deviations. We'll get into why you want to do that. Find the sum of those squares of the deviations from the mean. Divide that sum by 1 less than the sample size, n minus 1, and then take the square root of the result. So just to say this all at once, the sample standard deviation is the square root of the quotient of the sum of the squares of the deviations from the mean, and 1 less than the sample size. That makes it sound a lot more complicated than it actually is. I don't want you bothering to memorize this formula. As you might guess, I'm going to show you how to do this with the calculator. But one time I want to demonstrate how to do it by hand just to show you that this formula isn't that hard to use. It's not fun to use. Even for a small data set it takes quite some time, but it's not difficult. And I want to demonstrate it just once. It'll also give us an opportunity to talk about the bits and pieces of the formula and why we would do the things that we do. Let's do an example of a sample standard deviation by hand. I have these 5 pieces of sample data, 2, 3, 6, 9, and 15, and we're going to find the standard deviation of this sample. So I'm going to organize the first couple of steps into a table. I'm going to list the 5 values of the variable, 2, 3, 6, 9, 15. And now let me jump back to the formula. The first thing we want to do is this step inside the parentheses where we take each value of the variable and subtract the sample mean. Well, before we can do that, we have to find the sample mean. So off to the side, let me do that. The sample mean, which we denote by x bar, is the sum of the values in the set divided by the number of values in the set. So 2 plus 3 plus 6 plus 9 plus 15, that's 35, divided by 5, which is 7. So the sample mean is 7. X bar is the appropriate symbol because this is sample data. And now again, jumping back to the formula, we take each value of the variable and we subtract the mean in that order, x minus x bar. So we do 2 minus 7, which is negative 5. Then we do 3 minus 7, which is negative 4. And 6 minus 7 is negative 1. And 9 minus 7 is 2. And 18 minus 7 is 8. And we have our 5 differences here. We call these the 5 deviations from the mean. These represent signed distances from the mean. Signed because some are negative and some are positive. A negative distance here tells us that you're to the left of the mean, and a positive distance tells us that you're to the right of the mean. Normally in math, we say the distances must be positive. Right? In casual conversations, you wouldn't say I ran -2 miles today. Sometimes I feel like I could say that because my eating habits are equivalent to running -2 miles. But outside of stupid jokes, a negative distance doesn't make sense in that context. But a signed distance like this just tells you whether you were below the mean or above the mean. Now, an obvious thing to try would be to average these 5 numbers in some way. But if you take the time to add these, you'll see you get 0. And there's nothing special about the example that I chose. You'd get 0 every time you summed the deviations from the mean. So if we got rid of these negatives, we wouldn't run into that. And I guess we have 2 options for getting rid of negatives. We could take the absolute value. There is such a measure of variation. We call it the mean absolute deviation. Or we can do what the standard deviation does, which is to square each of those. When you square a negative number, you get a positive result. And when you square a positive number, you get a positive result. So that'll get rid of any negatives. And our sum won't come out to 0. So I'm squaring each of these deviations. -5 times -5 is positive 25. And I got the rest of those using similar arithmetic. Now this sum won't come out to 0. The only time this column could come out to 0 is if all of these numbers were 0. And that could only happen if the previous column were all zeros. And that could only happen if the original column was all the same number. And that's not a very interesting example, so we won't run into that. So we'll always get a positive sample standard deviation. Back to our formula. The sigma notation tells us to find the sum of those squares. So I'll do this off to the side. The sum of the squares of the deviations from the mean would be 25 plus 16 plus 1 plus 4 plus 64, which comes out to 110. And now we want to find an average of those deviations. We're going to divide by something. And this step might seem weird. We're going to discuss really quickly why we do this later. We're going to divide by 1 less than the sample size. So I'm going to take that sum and divide by 1 less than the sample size. So we got the sum of 110. There are 5 pieces of data, so we're actually going to divide by 4. And 110 divided by 4 is 27.5. And now it kind of feels like we're done because we did the division step. That should be the average. But there's something wrong. If you look at that number, it seems way too big for an average distance from the mean. You look at our sample data. The range is only 13, so there's no way the average distance from the mean could be 27.5. Why is this number so big? Well, it's because we squared everything. And how do you suggest that we get rid of that squaring step? You guessed it, we're going to take the square root. So the standard deviation is the square root of that quotient. And now the square root of 27.5 isn't a nice, neat number. It's definitely bigger than 5. We could probably ballpark it. 5.2 squared is 27.04, so it's going to be a little bit bigger than 5.2. If you push second and your x squared key, which is the 5th key down the left side, you'll get a radical. I have my calculator set up right now for the older operating system, which gives us a parenthesis. I type in the radicand, the number under the radical. You don't have to close the parentheses, but I can't help it. And there's our answer. It's around 5.244. Real quick demonstration of how that would look in the newer operating system. Those of you with a calculator running that newer system will actually see a radical when you hit second and the x squared key. And you just type the radicand underneath, and the little bar across the top will extend as you type. And then you hit enter when you're done. No need for parentheses. In fact, it would be incorrect syntax to add a parenthesis. And you get that same result of 5.244. Great. What does that mean? Well, standard deviation is a little bit harder to get a handle on than those averages, those measures of center from the previous section. But basically, this gives us an idea of how spread out the data is. Because the number is fairly small, it's around 5.2, it means that the data is fairly compact. It's pretty close together. And you might argue, well, why go through all that when you could just calculate the range and see that the data is fairly close together? I see your point, but if there had been an outlier in this set, the standard deviation would do a better job. Furthermore, the standard deviation can be applied in much more powerful situations. We'll be using the standard deviation in a few different applications throughout the semester, and it's its arithmetic property that allow us to do that. I want to discuss further this idea of understanding standard deviation, but before we do that, I want to get you off the hook here. I don't want you doing these standard deviations by hand. If it's up to me, this is the last one that you'll ever see done by hand, because even though it's not difficult, it just takes a really long time, even for a small data set. This only had 5 pieces of data, and it took us quite some time to knock that out. It's so much faster with the calculator. Let's run through that. Thankfully, this isn't that much different than calculating a mean or a median in the calculator. We're going to do the exact same example. Bring up the calculator. I'm going to leave our answer from last time on the main screen just so that we can compare the results. I need to enter the data into a list. Remember, we do that by pressing Stat and the 1 key. My list is already clear because my emulator resets every time I close it. If you need to clear your list from a previous example, use your up arrow to scroll to the list name, push the clear key, and the down arrow. Now we're going to input our data, 2, 3, 6, 9, 15. Note that it's asking me for a 6th value, so I must have typed in 5, so I'm good. I'm going to quit back to my main screen, second mode. To access the list screen, we push second and the stat key. We want to do some math, so I'm going to scroll to the left. And then if you look down the list, choice 7 says STDDEV, which is a common abbreviation for standard deviation. And in fact, this calculates the sample standard deviation. Again, the population standard deviation is done slightly differently, so it's important that you know that. I'm going to press the 7 key because I'm way too lazy to scroll all the way down there. It's asking me for the list name that I'm using. I'm using list 1, so second and the 1 key. Don't have to close the parentheses, but I can't help it. And then you hit enter, and it's the same result, way, way faster than doing the formula by hand. Even though the formula by hand wasn't hard, it's a pain. It's much easier to use the calculator. If you want to calculate a mean by hand, be my guest. But please don't do the standard deviation by hand because it's going to take you a really long time. The standard deviation is, again, around 5.244. Again, that represents an average distance from a value of the variable to the mean. So let's try to get a handle on understanding standard deviation. And we'll do this by looking at an example of 2 lists of data. I have the number of minutes it took for 2 different chains to deliver pizzas to a specific address. So for chain 1, it took 53 minutes the first time, then 35 minutes the second time, and so on. For chain 2, it was 48 minutes the first time, 40 minutes the second time, and so on. What I'd like to do is calculate the standard deviation for each of these 2 sets of data. These are samples. So I'm going to call the standard deviation S. Now I'm going to walk you through the steps for each of these. But if you feel comfortable, you should really try doing it on your own. Or watch me do it once, pause the video, and then see if you can do it on your own after seeing me do it. You want to get comfortable with this calculator because we're going to be relying on it so much. So for chain 1, I'm going to go to the lists, stat, choice 1. I'm going to clear out the old list by pushing the up arrow, then clear and the down arrow. And now we're going to type in these delivery times. 53, 35, 62, 27, 43, 71. I quit back to the main screen with second and the mode key. I press second stat to bring up the list options. Scroll to math. Choice 7. Enter the list name. Close the parentheses. I guess you don't have to do that. Hit enter, and I get a standard deviation of around 16.63 minutes. Again, it's hard to interpret what it means on its own, but basically it's the average distance from a value of the variable to the mean for that chain. Where we can make a lot more sense of this is when we use it for comparisons. Let's compare that to chain 2 and then talk about what these standard deviations mean in comparison with one another. Let's enter the data for chain 2. I go back to the lists, stat, choice 1. I scroll up to the list name, push the clear key and the down arrow. Now I input the second list of data. 48, enter. 40, enter. 51, enter. 47, enter. 52, enter. 47, enter. Now I didn't have you gauge this before we started, but if you look at this list that we just put in and compare it to the previous list, you might notice that these delivery times are significantly more consistent than the previous chain. I want you to think about what that's going to mean as far as the standard deviation. Make a prediction for whether the standard deviation will be bigger or smaller than the standard deviation for chain 1. I quit back to the main screen with second in the mode key. I use second stat to pull up the list options. Scroll to math. Choice 7. Second in the L1 key. Close the parentheses. Again, you didn't have to do that, and again, I can't stop myself from doing it. Hit enter, and we get a standard deviation of only around 4.23. Now again, when I tell you that that number represents an average distance from a value of the variable to the mean, maybe that doesn't make a whole lot of sense. But when we compare the two standard deviations, you get something that's a lot more natural. Because the standard deviation for chain 2 is smaller than the standard deviation for chain 1, that indicates that the data for chain 2 is much more compact, much closer together than the data for chain 1. And you can see that just by eyeballing it. Chain 1's data ranges from a high of 71 to a low of 27. And chain 2's data ranges from a high of 52 to a low of 40. A standard deviation on its own can be hard to understand. A standard deviation compared to another standard deviation is much more natural. The bigger the standard deviation, the less consistent the data. So in this specific example, if you know you want your pizza in around 45 minutes or so, chain 2 is a safe bet. Their standard deviation is small, the average is somewhere in the 40s. You know you're going to be getting your pizza in 45 minutes or so. If you want to roll the dice with chain 1, you could get a really fast delivery time, you could get a really slow delivery time. They're not as consistent with their delivery times, and you can see that reflected in the standard deviation. Hopefully this example helps solidify what standard deviation tells us. I want to get into one application of standard deviation, but before we do that, I've mentioned a couple of times that population standard deviations are calculated slightly differently. First, a bit of notation. A population standard deviation is denoted by the lowercase version of the Greek letter sigma. The way I draw it kind of looks like a cursive O. You might want to look at one that's been typeset either on a computer or in your textbook to see exactly what it should look like. Just like with means, we use a Greek letter for the parameter. And you'll notice that the formula is similar, but looks a little bit different in one place and actually is different in another. You still take the square root of a quotient. You still take each value of the variable and subtract the mean, although this time the mean is denoted by mu because it's population data. You still square all of those and add, but you divide by the entire population size. You don't subtract the 1. Now, just a real quick smoke and mirrors explanation for why we subtract 1 in one place and not the other. If you want a more detailed explanation, I encourage you to hit up your textbook for that info. But here's the basic idea. This formula was actually the first one that was invented. Somebody wanted a way to measure variation in a set, and they came up with this formula. It's a natural way to do it. Then they started thinking about how you could estimate these using statistics, like the sample standard deviation. And they noticed that when they divided by the entire sample size, their estimates weren't as good as they were when they subtracted 1 from the sample size. They just noticed this empirically. They noticed that if they were to subtract 1 from the sample size and use the formula that we talked about earlier for their estimates, they got a better estimate than when they just divided by lowercase n, the entire sample size. Some other nerd later proved that you get better estimates by using this, and so it's just been agreed on that the sample standard deviation should be calculated by dividing by 1 less than the sample size instead of the entire sample size. If you find that conversation interesting, first, I feel sorry for you, but secondly, you can follow up on it by looking in your book. The book has a brief discussion of that idea. Where this is important to you is that you have to understand that if you're calculating a sample standard deviation with the calculator, you'll get one result, and if you calculate it as though it's population data, you'll get a different result, and we'll discuss that when it comes up. For now, let's get back to understanding standard deviation. Along with this comparison of variation of two different sets, we also use standard deviation in other applications. For example, it's part of the formula for what we call a z-score. The z-score of a piece of data is the signed distance from a value of the variable to the mean measured in standard deviations. That's the important part. We measure the z-score not in the units of the original variable, but in standard deviations. This is a way to norm out differences in two sets of data. We're going to make this a guessing game. Let's see if you can get it. A z-score is denoted by anyone? Anyone? Yep, z. We use the letter z to represent a z-score. So how do you calculate a z-score? Well, it's a signed distance from a value of the variable to the mean. We already know how to do that. You take the value of the variable and you subtract the mean, deviation from the mean. But how do you measure it in standard deviations? Well, you divide by the standard deviation. So the formula for z-score with sample data is x minus x bar, the sample mean. That gives us the signed distance from the mean. And then we divide by the size of the standard deviation of the sample. That converts it to standard deviations. Or, if you're working with population data, it's x minus mu, the population mean, divided by sigma, the population standard deviation. This again converts this signed distance from the mean to a number of standard deviations. Z-scores are nice for trying to make comparisons between two sets of data that have something in common but maybe are on different scales or just fundamentally different in size. So let me give you a couple examples of that. Most of you are probably aware that there are two common standardized tests for determining college readiness. There's the ACT and the SAT. The ACT is scored on a scale up to 36, where the SAT was scored on a scale up to 1600, and then they changed it so that it went up to 2400, and I don't know if they changed that back or not. But they're scored on much different scales. It doesn't make sense to compare the size of an ACT score to the size of an SAT score. Like if you said you got a 35 on the ACT and somebody else got an 800 on the SAT, you can't say, well, 800 is bigger than 35, so the 800 is the better score. That doesn't make sense because they're on different scales. How could you norm out the scales that they're on? Well, you could use z-scores. Z-scores will take the scale into account. That's how you might apply a z-score. Another scenario where you might use that is when you're comparing two distinct populations using the same scale. So as an example of that, I'm 5'8", so for an adult male, I'm below average. I'm short. I'm considered short relative to my population. Suppose I was standing next to a 4'3"-year-old. A 4'3"-year-old is gigantic. Relative to the population of that person, they are very, very tall. Relative to my population, I'm actually a little bit short. Can you hear the defensiveness in my voice when I say a little bit short? I'm short. I should just own up to it. I'm short. If you were to compare me to a 4'3"-year-old, I'm literally taller than that person. But nobody would call me tall, and nobody would call that 3-year-old short, because relative to our populations, I'm short and that person's tall. A direct comparison doesn't make sense. Rather, we want to compare to the population from which we come, and z-scores do that. Let me show you some examples. In the first example, we have some prices of silver rings. So there are two different retailers. Retailer 1 is a little more upscale. Their average silver ring costs $1,000 with a standard deviation of $600. So much more expensive and much more varied. Retailer 2, more affordable. Their average silver ring costs $250. Not as much variation as the standard deviation is only $100. Here's my question. Which ring is relatively cheaper? Or another way to say this is, which one is the better buy? An $800 ring from retailer 1 or a $200 ring from retailer 2? This is something people talk about quite a bit. You'll hear somebody say they paid $40 for a shirt from a specific store, and your brain might go, oh, that's cheap for that place. $40 for a shirt seems expensive to me. But that's because I shop at places where shirts cost $10, $8. I'm not paying a lot for a shirt. I'm a math guy. I'm allowed to look like a dork. But I still understand the idea that that store has really expensive shirts and $40 might be cheap for that store. That's the kind of comparison we're making here. Obviously, $800 is more than $200. But I don't want to know which one is absolutely cheaper. I want to know which one's relatively cheaper compared to its population. The $800 ring from the more expensive store or the $200 ring from the less expensive store. We can do this using z-score. The z-score formula says find the sign distance from the value of the variable to the mean and then divide by the standard deviation. So for retailer 1, which I'll not so cleverly denote by R1, I take the value of the variable, the $800 ring, I subtract the mean for retailer 1, which is 1,000, and I divide by the standard deviation, which is 600. So I get negative 200 divided by 600, and that doesn't come out perfectly. That comes out to a negative 0.33 approximately. I've rounded that to the nearest hundredth. Comes out to negative 1/3. I've rounded that to 2 decimal places, which is kind of the traditional place to round a z-score to, is the hundredths place. This negative 0.33 isn't measured in dollars or hundreds of dollars. It's measured in standard deviations. So this answer is saying that a ring of $800 from retailer 1 is about 0.33 standard deviations below the mean. Less expensive than the average. Let's compare that to retailer 2's ring of $200. So I take the $200 value of the variable, I subtract the mean for retailer 2, and I divide by the standard deviation for retailer 2. That's negative 50 divided by 100, and this one actually does come out nice and neat. It comes out to negative 0.5. A lot of people will still write the 0 out of habit, just because there's this tradition of using 2 decimal places for a z-score, but we don't need to do that. This indicates that this is about a half of a standard deviation below the mean. So which ring is relatively cheaper? Well, the $200 ring is a half of a standard deviation below the mean, where the $800 ring was only a third below, and so it's the $200 ring that's cheaper. The cheaper ring in this case will be the one with the smaller z-score, and that's the $200 ring from retailer 2. Let's look at another example. We're going to compare basketball players who play in different leagues. Those of you that follow sports know that the league in which you participate in can have a lot to do with the stats that you're able to compile. So in this basketball example, we've got 2 players who are playing in 2 different leagues, and so it might not be fair to compare them straight up, because the style of play could be different, because the officiating could be different, maybe they even have different rules that affect the flow of play, and so we're going to compare these 2 players not absolutely against one another, but rather relative to the leagues from which they come, and see which one has the better performance. So player 1 is scoring 20 points per game in a league where the average is 12 points per game with a standard deviation of 8. Notice that I used the abbreviation for standard deviation here to save space. Player 2 is scoring 18 points per game, obviously lower, but coming from a league where the average is 10 points per game with a standard deviation of 6. Yes, player 2 isn't scoring as many points as player 1, but they're coming from a league where the average scoring is lower. The players score less on the average. You can't even compare each player to the average solely because both are scoring 8 points above the average. So we're going to go to z-scores and take the standard deviation into account. For player 1, the z-score is the 20 points per game that they are scoring minus the mean for their league divided by the standard deviation for their league. So that's 8 divided by 8, which even I can do, that's 1. So 1 standard deviation above the mean. Better than average because it's a positive z-score, 1 standard deviation above. Player 2 is scoring 18 points per game. In that league, they're averaging 10 points per game, and the standard deviation is 6. That's 8 divided by 6, which is around 1.33. Again, rounding to the nearest hundredth because it's tradition. Also above the mean, but further from the mean. More units above the mean. Because player 2's z-score is larger, they actually have the better performance relative to the league from which they come. Yes, they're scoring fewer points overall, but they're coming from a league with a smaller average and a smaller standard deviation. There's less variation. So scoring that many points above the mean is actually more difficult in that league than it is in Player 1's league. Because of that, according to Z-scores, Player 2 has the better performance. You can see in this example that the standard deviation was really what told the story, because the difference between the value of the variable and the mean was the same. They're both scoring 8 points above the average, but the standard deviation is how we distinguish which one actually has the better performance. So I hope this gives you an idea of what standard deviation is and how it can be applied. This section is going to take some practice, and not just using the calculator, but also getting a handle on what standard deviation is. If you have any questions, don't hesitate to contact me.